going to talk about our novel probabilistic machine learning algorithm for sequential pattern mining. It defines a simple probabilistic model over transactions and uses expectation maximization to infer the most interesting patterns in the data. Our aim is to find the most interesting sequences in a dataset. Patterns that are most relevant to a data analyst doing exploratory data analysis. And for example, these might be the most prominent sequences of mouse clicks from a weblog, or in the example I've got here, API usage patterns. So suppose we're given sequences of method calls to a specific API, so for example, Twitter, and we want to find the most interesting subsequences of calls. So that is those calls that correspond to the most interesting API usages. And as you can see in this example, we've mined a common API call sequence that's used to set up a Twitter client. The first two calls initialize the client, and the second two set up authentication. So why interesting sequences? Well, the early work on sequence mining was based on frequency. But actually, it turned out that frequency is a very bad measure of interestingness. This is because any subsequence of a frequent sequence is itself frequent. Then mining frequent sequences leads to huge redundant sets and also pattern explosion. And for this reason, sort of recent modern approaches to sequence mining have been developed. And these measure the interestingness of the set of patterns as a whole. And in doing so, are largely able to avoid uncorrelated patterns. And the most recent and successful of these are compression-based methods. And these find the set of patterns that best compresses the data based on an encoding scheme. So these define an encoding scheme that's based on a code table that maps patterns to their codes. And so in this example, we've encoded the two patterns A, B, C, and DA using the codes P and Q, respectively. So we take a slightly different approach to this. What we do is we define a generative probabilistic model that allows us to infer directly the most interesting sequences in the data. And the main advantages of this approach are that, well, firstly, we have an implicit encoding scheme given by the model. We can also easily incorporate prior knowledge into the model in the form of a prior. And also, we can easily compose the model with other probabilistic models of the data. So let me give a brief overview of our approach. So we start with a set of interesting patterns I. So supposing we have this set, we can then define a probabilistic model that generates a transaction in our data set from this set of patterns I. And if we make this model relatively simple, this means that the statistical correlations that are present in the data will largely be explained by the interesting patterns themselves, not by the model. And then once we have this model, we can then infer the best set of patterns under this model using some statistical inference algorithm. So let me give, first of all, a probabilistic model for item sets to illustrate our approach. So we can fully describe the model in terms of how it generates a transaction from an initial set of interesting item sets and associated probabilities. So in this case, I've here got three item sets, each with an associated probability. And for each of these item sets, we simply flip a coin to decide whether to include it in the transaction or not. And so here, the coin flip is essentially a binary variable that denotes inclusion. And so in this case, we've chosen to include the first and third item set, but not to include the second one. And we then set the transaction to be the set of all the item sets that we've chosen for inclusion. So in this case, S1 and S3. So here's the formal description of the model's generative process, which is independent for each transaction. So independently for each transaction, we flip a coin for each interesting item set and include those that are selected. So the coin flip ZS is just a draw from a Bernoulli distribution. And then the transaction is just the union of all the item sets that have been selected for inclusion. So a relatively straightforward model. So assuming all the model parameters have been determined, we can then write down the probability of a transaction x under the model, and that's just the probability distribution of Bernoulli. If we know the actual probabilities pi, we can then infer the binary inclusion variable z by maximizing the model likelihood. And it turns out this is actually a set cover problem. We want to cover the transaction with our interesting item sets. And now, if all the parameters of our model are unknown, and this is the real-world case we're actually interested in, then we can infer them using the expectation-maximization algorithm, which I will explain in due course. But now, let me give the model for sequences. So as before in the item set case, we can fully describe the model in terms of how it generates a transaction from a set of interesting sequences and associated probabilities. But this time, the probabilities tell us how many times we want to include the sequence in the transaction. And so for each interesting sequence, we flip a coin, again, this time a 3- or 4-sided coin, to decide how many times we should include the sequence in the transaction. In this case, we've chosen to include the first sequence once and the third one twice, but not include the second one. And then we then set the transaction to be a possible interleaving of the included sequences. Sorry. So what do I mean by interleaving here? Well, you can see from the example, we've selected sequence S3, which is the singleton E in red here, to be included twice. And what we do is we interleave that red E in amongst the sequence S1, which is in blue. And you can see our end transaction is B, then E from the third sequence, C, E, and then again E from the third sequence. So that's what I mean by interleaving. So here's the sort of formal description of the generative model for each transaction. So first of all, we sample the multiplicity ZS from a, this time, categorical distribution. And then we can sample the transaction X from P, where P here is the set of all possible interleavings of the sequences that have been chosen for inclusion in the transaction. So that's those sequences which have ZS greater than or equal to 1. And you can see here that all the possible interleavings of the singleton sequence C in amongst the sequence AB. And you can see there's, in this case, 3 of them. So this time, the probability of a transaction under the model is a categorical distribution divided by the size of P. That's the set of all possible interleaved sequences. And much like before in the item set case, if the probabilities are known, we can infer the categorical inclusion variable Z by maximizing the model likelihood. And as before, this is also a set cover problem. So this time we want to cover the transaction with sequences, allowing gaps between the sequences. And if all the parameters are known, if all the parameters are unknown, as is the real-world use case, essentially, we can infer them using expectation-maximization. So in our case, the expectation-maximization algorithm is just a simple layer on top of the set cover problem. So we alternate between 2 steps, the E step and the M step. So in the E step, we estimate the inclusion variable Z given the probabilities pi that we've calculated in the M step. And in the M step, we estimate the probabilities pi given the inclusion variable Z that we've calculated in the E step. And we alternate these 2 steps until our parameters converge. Now, to add candidates into our model, we use a variant of EM called a structural EM. And this allows us to suggest candidates at the same time, and including those candidates that improve the model's likelihood. So that's, in fact, the average likelihood across all transactions in the database. And so the main difference here is that in the E step, we add a new candidate S prime to the model with an initial probability of being included in the transaction of 1 so that it's used in as many transactions as possible. And then we calculate its actual probability in the M step. And this allows us to calculate a probability for the new candidate S prime, and therefore to then calculate the likelihood and determine if the likelihood is improved, so if this candidate is worth including as an interesting sequence in our model. So how do we generate these candidates in the first instance? Well, we do this sort of a priori style. We recursively combine the interesting sequences that we have so far with the highest supported ones first. And you can see from this example here, we're combining A and BC to give ABC, and also to give BCA, and then A and D to give AD and DA, and so on and so forth. And the main advantage of this approach is that you can see very quickly we can generate very large sequences of interest. However, there is a slight problem in calculating the model likelihood in that it requires calculating the size of P here, which is the number of possible interleaved sequences. And of course, this is impractical. And so we need an approximation. But luckily, we can actually bound the size of P from above by all the possible permutations of the items in P. So effectively, we're treating P as a set of singleton sequences. And this gives us a lower bound on the likelihood given here, which we can then substitute back into our likelihood equation here. So we can replace the minus log P at the end there with our bound. And this makes the calculation practical now and efficient. So to sort of bring it all together, our complete algorithm for interesting sequence mining, ISM, is then the following. So our algorithm takes as input a list of transactions x1 to xn. And it starts by initializing the set of interesting sequences with all the singletons that are present in the data and initializing their probabilities with their supports, so the number of times they occur in the data set. And it then alternates between adding new sequences into this set of interesting sequences I, so specifically adding those sequences that improve the model likelihood using structural EM, and optimizing the probabilities, the parameters of our model pi, using standard EM. And we do this, sort of iterate these two steps, until we exceed some user-defined iteration limit or time limit. And in order to rank the interesting sequences under our model, we've also developed a novel measure of interestingness, a novel ranking function, essentially. And we define this as the ratio of transactions that the sequence explains under the model to the transactions it supports, breaking ties using the sequence probability pi s. And you can see here that this is just the number of transactions that a sequence S has been chosen to explain, so the number of transactions for which the inclusion variable ZS is greater than or equal to 1, divided by the support of the transaction. So that's the number of times it occurs in the data set. So that's our algorithm. But now let's put it into the context of sort of existing work in the field. So I mentioned before the sort of compression-based methods. And these methods make use of what's known as the minimum description length principle. And what the minimum description length principle does is it says that you want to choose the encoding scheme that best compresses your data. It's as straightforward as that. But there is actually a correspondence between the minimum description length principle that these compression-based algorithms use and a probabilistic model. So specifically, if we have an encoding scheme that assigns each pattern x to a description length Lx, then this is equivalent to a probabilistic model, which is 2 to the minus Lx, that's the description length, for which E is optimal. And this is essentially just Shannon's theorem. And so our method is essentially equivalent to the approaches that have come before. So the sort of two main MDL-based approaches for sequence mining are GoCrimp and SQS. And here are some of the differences between our approach and theirs. So specifically, our model can handle sequence interleaving directly without having to encode the sequence positions in a code table, which can take a lot of housekeeping. Also, it doesn't need to punish large gaps in sequences, although this is something we can incorporate if we would so wish. Also, we have regularization that's built in directly to the model, so we don't actually need to define an explicit so we don't actually need to define an explicit regularization scheme. And also, there's no need to define an encoding scheme, because that comes from the probabilistic model itself. So let's look at the results of running our algorithm on a variety of real-world data sets. So here I've got 4 real-world data sets: the text of Alice in Wonderland, some transactions from an e-commerce website, so essentially market basket data, the abstracts of, from the Journal of Machine Learning Research, so abstracts of papers in the Journal of Machine Learning Research, and also a database of sign language utterances. And you can see these data sets are quite varied. They have a sort of number of items that vary from about 200 to 4,000, and numbers of transactions that vary from about 200 to about 700 to about 60,000. And as you can see, ISM performs quite well on these data sets, returning a good number of interesting sequences in a reasonable amount of time. So let's take a look at the redundancy of ISM compared to SQS, GoCrimp, that's the compression-based approaches, and BID, which is a closed frequent sequence miner. And so what we did here is we measured the redundancy of the top 50 sequences returned by each of the algorithms using the average edit distance between them. And the first thing that you immediately notice is that the closed frequent sequences mined by BIDE are highly redundant, differing by just 1 item on average across all the data sets. ISM, on the other hand, is the least redundant of these, sort of on 3 of the 4 data sets, with SQS not far behind. And GoCrimp struggles to return 50 sequences on 2 of the data sets, but otherwise it's roughly comparable to SQS on the other 2. So looking at the top sequences returned by ISM from the text of Alice in Wonderland here, we can see that we get collocated words and phrases such as mock turtle, went on, as well as correlated punctuation such as open bracket, close bracket, and open quote, close quote. SQS and GoCrimp, on the other hand, seem to be picking up a lot of sort of extraneous punctuation. So we're getting full stops towards the end of some of the phrases, or commas at the beginning of some of the others. And finally, going back to our motivating example from the beginning of mining Twitter API calls, we can see how a variant of ISM performs compared to 2 competing approaches, Mapo and UPMiner. So if we look at the top 5 patterns mined by each algorithm, we can see that ISM returns 2 main types of Twitter initialization call, highlighted here in blue. And you can see, however, that the competing approaches mostly return subpatterns of these 2 calls. And actually this, like for example, we have Twitter factory get instance, Twitter set consumer. So we're trying to get the instance of the factory, but we haven't actually initialized our factory, and that's not actually valid code. And this isn't really surprising because these other approaches are based on frequent sequence mining. So we'd expect that their pattern sets be quite redundant. So in conclusion, I've presented the first probabilistic algorithm for a generative algorithm for sequence mining. This algorithm applies to other patterns, not just sequences, also to item sets, API calls. It's very closely related to the existing MDL, compression-based approaches to sequence mining. And I've also shown that it mines more diverse sets of patterns than the other approaches. So the code for all our algorithms and the datasets are available to download from our website. Thank you for your attention.
Questions?
Hi, Charles. Thanks for an excellent talk. You state that one of your objectives is to reduce the to minimise the redundancy in the set of patterns.
Yes.
I'm just interested to hear your reasoning for believing that. Well, I'd be interested to hear whether you believe that that's always desirable or only in some applications. So, for example, in the Alice case, say Queen and Hearts might be a pattern that you'd be likely to pick up, and perhaps Queen Mad Hatter might also be a pattern you might pick up because they turn up together a lot. But there's redundancy there because Queen turns up both times. Why does that matter?
Right. I guess it depends what you mean by redundancy here, right? So in that case, I wouldn't say the patterns there are redundant. They're both strongly correlated, right? So I'd say they're not. But there are cases, and essentially what we want to avoid is situations where you have one long pattern, and then you have lots of combinations of the patterns, like you get with frequent sequence mining, which actually aren't correlated at all. They only exist because both patterns are very frequent. If you see what I mean.
I do indeed see what you mean. So in that case, I'd like to present a counterpoint to your viewpoint. So you're presenting the crimp-style approach to pattern mining applied to sequence mining, and the crimp-style approach selects one model that best compresses the data. And that's a very powerful and useful approach, but it does have a limitation that it only selects one model, and in many contexts there are likely to be many alternative models, each of which are probabilistically indistinguishable, and it's arbitrarily choosing one, and it's not even warning you about the other alternatives or what they are. And there is an alternative approach, a modern approach, that has successfully been applied to pattern mining. So as Tati did publish last year and Petitjean et al. This year, which applies my approach to pattern mining, which uses consideration of all partitions of a set to check for the interdependency that you're saying that we should avoid. And so in the case of sequence mining, you look at all partitions into two subsequences. So it's not a criticism, it's just pointing out there is an alternative stream of work which also is successful but has different objectives to yours.
Sure. And in some sense, our work could incorporate something like that because we're taking this probabilistic approach. We have a probabilistic model. We can take several models, each different ways of doing the compression, and combine them in a Bayesian rigorous way. And then we have something like you alluded to.
Very nice talk. My question is about, do you think this approach can also be applied to tree mining and graph mining?
So we've looked at applying it to tree mining, but the main problem with tree mining is that the inference procedure, if I go back to the inference slide, is set cover. So we're covering the transaction with sequences, right? Now, in order to do that, we need to be able to know, is this sequence contained, subsequence contained in the sequence? Now, for sequences, that's fairly easy to do.
Right.
But for trees, we have to do subtree isomorphism, and that's actually very expensive.
Yeah.
And that's the difficulty with doing that approach. So if there was some way of doing approximate subtree isomorphism, then I think this would certainly be a lot more viable. But at the moment, yes, it's possible, but it's a little slow.
Thank you.
Two questions. The first one is, possibly I understood incorrectly, but it seems that your generative model assumes that patterns are independent.
Yes, that's correct.
And maybe this is why you tend to find distinct patterns with little redundancy, regardless of whether this is a good idea or bad idea. I'm not saying, I'm just curious. Second question is, there is some work in the in the programming language community about detecting, inferring, and even further integrating patterns of API calls. I know at least two practitioners, Eran Yahav and Alon, I forget, sorry. So they do similar work, and they extract much more meaningful sequences because they take the semantics of the program, semantics of the language into account. So I wonder if you compare this to their work, or at least have a look.
So no, I haven't. I'm not familiar with their work. So our limitation here is that because it's a sequence mining approach, we need a sequence, right? So sure, we can use more complicated forms of data. So here it's just the method calls themselves. I mean, we could augment that with other information, but ultimately we're limited by the fact that it needs to be a sequence of statements of call, some sort of statement.
So maybe for your specific use case, perhaps.
Yeah.
All right, thank you.
Any other question? So let me check again. I still want to check again. Is any author of the Fowkes paper here? No? Okay. So that's the speaker.